Okay. Next up, we have Eleonora. Uh, she's a postdoc at TU Wien. She did her PhD at Oxford. And among other things, she's made strong contributions to AI safety by constraining learning methods using logic. Take it away, Eleonora.
Hi, everybody. Thank you, Alexander, for your very nice introduction. And I'll share my video. Screen. So does everybody see my screen?
Yep.
Okay, perfect. So hi, everybody. I'm Eleonora, and today's talk will be about deep learning with logical requirements. Before starting, I would like to give a big thanks to all my collaborators that essentially made this work possible. So just a quick outline of the talk today. I'll start by giving an introduction, which will be essentially an overview of my vision of the problem and where I think neurosymbolic AI and machine learning should go in the coming years. Then I'll give an introduction to the models that we have introduced throughout the years for deep learning with logical requirements. I will then introduce the benchmark that we have actually created to test models. And finally, I'll wrap up with some take-home messages. So let's start with what is the big problem. I think the problem that I tried to solve is a problem that everybody is trying to solve, which is that deep neural networks have been responsible for state-of-the-art results for many years. However, they can still exhibit some behaviors and make mistakes that what we would call normally an intelligent being would never commit. Some of these mistakes are actually so bad that they make the news, and this really hinders the trust in the general AI of the public. So, obviously, at the beginning of my research career, I started with a big question: how can we solve this problem? Then, as I went on on this journey, I realized that maybe this was a bit too big of a question, and so I changed it to how can we at least alleviate this problem. And I would like, again, since I would like to give here a vision of what I would like to do, I would like to start with a high-level view. So let's have a look from a high-level perspective to the standard machine learning pipeline. So what would you do when you would like to create a standard machine learning model? Well, you would take your own data, collect it, curate it, or just take a standard data set. Then you would create a model, train it, test it, and finally deploy it. Now, let's compare with standard pipeline with what is the standard software development pipeline. Here below, I just plotted some of the most standard software development pipelines that you can find in any software engineering book. So we have the waterfall pipeline, the agile software development pipeline, and here we have the spiral pipeline, which is a bit more complex. So what have all these pipelines in common? What really catches your eye? Well, what at least catch my eye when I started studying machine learning as an engineer, let's say, was the fact that in all software development pipelines, you always start from a very basic step of requirement elicitation. And once you have your requirements elicited and well defined, then you can essentially model your entire software on the ground of the requirements that you have defined. As you can see, this step is actually missing in machine learning. So in a very recent position paper that I wrote with some colleagues, we basically propose to move away from the standard like machine learning development pipeline and towards a more requirement-centric one. So this is actually a very high-level development pipeline that we propose, where, as you can see here, you have all the standard steps that you would follow when you have a machine learning pipeline. However, all of these are preceded by a requirements definition step, which, as you can see from these lines, are actually there to shape and model each of the subsequent steps. Further, we also think that it would be really important to sort of get in the mentality of if there is any problem at any steps here, we should reiterate back to the requirements definition itself, because sometimes, like especially in model training, I feel, if there is any problem, we just keep changing like paper parameters or the tuning and things like this. But sometimes we would need probably to go back to the requirements definition themselves and maybe change, for example, our data or the design of the model itself. So this is like the high level view of what I think could help in at least alleviating some of the problems that we are experiencing now in machine learning. Now, this is still very high level, one could say. So the next question is, okay, this is good vision, but what can we do in practice? So this leads to the more technical research question that I've been posing myself in these years, which is it possible to build neural networks that are guaranteed to be compliant with a set of requirements by design, ideally, while at the same time learning from the requirements themselves? And this second question is very important because I feel like a lot of times people think of requirements as simple guardrails that are there, yes, to make machine learning safer, but at the same time, like they are a way of, they hinder the performance. However, I strongly believe that the requirements are expressing background knowledge, and if we learn how to exploit them in a smart way, then we can actually exploit the background knowledge and create models that are actually much more competitive. So, after quite some years of research, I can answer to this question and say, yes, we can do these two things at the same time. So, let's have a look at how. I would like to give you a very quick intro on how. And I won't be able to get into all the details, so we will look into this problem with a very simple example, and then which will give you the intuition, basically the basic building block, to then go on with the other models. So suppose you have two classes, A and B, okay? So you have a very basic problem with two classes A and B, and suppose you have a very simple requirement, which is, you can read it as A implies B, but basically is saying, okay, if whenever you predict the class A, then you should also predict the class B. Also, to visually aid ourselves, suppose that the dataset is distributed in this way. So how do you read this? Essentially, here we are saying a data point belongs to the class A if it falls in this rectangle, and it belongs to the class B if it falls into either of these rectangles. As you can see, so this is the same data set, it's just a representation of the class A and the class B. And as you can see, the ground truth is actually compliant with the requirement, right? Because whenever a data point belongs to a class A, it belongs also to the class B. How would you approach this problem with a standard approach? You would take a standard neural network. Here I plotted a feed-forward neural network. And then this network would have two outputs, which we call H of A and H of B. And then you would train this with, let's say, a binary cross-entropy loss. Now, what is the problem with this approach? Well, first of all, there are no guarantees that the requirement is actually satisfied. And also there is no exploitation of the knowledge, right? Because the neural network needs to learn about this requirement. So to actually also give an idea of how a very tiny neural network would do, we implemented a very simple neural network with one in the layer and 7 neurons. And these are the decision boundaries that we get. How do you read these plots? So the bluer a region is, the more confident the neural network is that a data point falling in that region actually belongs to the class. And the redder it is, the more confident it is that it doesn't belong to the class. What can you notice from these two plots? Well, first of all, you can see that, for example, in this corner over here, the neural network is actually violating the requirement, right? Because there will exist a threshold for which the class A is predicted, but not the class B. Okay. Further, you can see that since we have have a very tiny neural network, then the neural network is actually struggling to learn the two rectangles. So the question is, can we do better than this? Well, thankfully, yes. So what we can do, our intuition was to build a max constraint module on top of a neural network. What does this module do? It just follows these two equations over here. So it's a layer without any neuron at all, but just does a maximum. So how to read this? The final output for the class A will be equal to the output that the neural network gives us. The final output for the class B will be equal to the maximum between the output for the class B and the output for the class A. So, what is the advantage of this approach? First of all, this ensures the satisfaction of a constraint. However, this has a downside, which is it can cause wrong supervisions. What do I mean by this? Suppose you are in this situation. So you have that the output for the class A is greater than the output for the class B. So what happens here? Here it happens that the final output for the class B will be equal to h of A, right? Now suppose that the ground truth for A is 0 and the ground truth for B is 1. Now, since the maximum is returning the output for A, if we use a standard binary cross-entropy loss, effectively what we would teach the neural network would be to increase the output for the class A instead of decreasing it, right? So this is actually a problem. Can we solve it? Well, thankfully, yes, with a very simple modification of the binary cross-entropy loss. So this is the loss that we would use in this very simple case. Now we'll break it down to have a clearer idea of what happens. So for the class A, as you can see over here, you have the standard binary cross-entropy loss. So nothing changes. Class A is fine as it is. For the class B, we have some changes. Let's again further break it down. So if the ground truth for B is equal to 0, then we go back to the case of the binary cross-entropy loss, so we are fine. However, when we are in this case, so when the ground truth for B is equal to 1, then we actually have some problems. So what do? We simply multiply the output for the class A times its own ground truth. This would allow the ground truth, which is when it's equal to 0, to return 0 over here, and the maximum would return again the output for B, thus fixing the entire problem of wrong supervisions. So let's see now how this would work on our very simple example. So I'd like to remind you, these are the decision boundaries that we get with a standard neural network. And then what we did was to implement exactly the same neural network, same hidden layer, with just our additional layer and loss. These are the decision boundaries that we get. Now, one would ask, how is it possible that you get these decision boundaries if you're not adding any weights? Because our layer doesn't have any weights, we are using the same neural network. How is it possible? Well, to understand this phenomenon, we need to look at what happens before and after the layer. So this is the decision boundary after the layer. Sorry. This is, on the other end, the decision boundary before the layer, so before doing the maximum. As you can see, the class B learns, since there is the maximum, that it doesn't need to relearn to put the output equal to 1 for these data points. But what we say is that it can delegate the prediction to the class A. So essentially, our layer is informing the neural network that A is a sufficient condition for B. And thus, the neural network doesn't need to learn any redundant information. So essentially, our method is just a more efficient way of using the same amount of neurons. Now, one critique that one could do would be, Okay, but it's not always convenient to delegate, right? Suppose you have the rectangles in this, like posed in this way. In this case, we have that the rectangle for the class A is the tiny one over here, and the rectangle for the class B is the bigger one. So what would happen in this case? Well, thankfully, our neural network is able to actually learn the right decision boundaries, right? And let's have a look at what happens before the layer. As you can see, the output before and after the layer is actually unchanged. Why? Because the neural network, even though it knows that A is a sufficient condition for B, doesn't need to use this sort of knowledge. It can use it only when it's convenient. Actually, here we have taken the two extremes, but we have done a bunch of experiments in the paper if you're curious with rectangles in different positions, where basically we show that the neural network can decide when to delegate the prediction and when not to delegate it. So this is essentially the basic building block of the entire framework that we created. Now, one would ask, okay, now we have done an example with just one constraint. Does it work with n constraints of the type always A implies B? The answer is yes, and it's also very, very easy to implement it on a GPU because the max constraint layer will be just the maximum operation between the output of each class and the output of all its own subclasses. So this is enough. For the loss, again, it's very easy because you can use the standard binary cross-entropy loss and just do this tiny modification over here, which is again just a maximum operation and a multiplication times its own ground truth. So again, very easy to implement on a GPU, which would be just 2 or 3 operations. So this is very efficient. So this scales with an hierarchical constraint. Sorry, I forgot this. So this I just show this very quickly, the experimental analysis. This is a big table that normally I put in all my presentations because we have tested our method on 20 hierarchical datasets, which are these. And these are datasets with hundreds of classes and thousands of hundreds of constraints and thousands of classes. And essentially all of these four were very complex methods, one could say, that were tailored for these datasets. And we managed to beat all of them with simply a feed-forward neural network with 2 layers and our method built on top. So the takeaway point of this slide was simply to show that even in practice, sometimes it's more convenient to include the background knowledge and instead of creating maybe super complex architectures. Sometimes it's enough a feed forward plus the background knowledge that you have. So going back to the initial topic, the natural question then would be, can the same intuition be extended to more expressive requirements? The answer again is yes. A lot of yes answers after 5 years of doing this research. So what we were able to do was to basically solve problems which entailed requirements written as stratified normal logic rules. What is a normal logic rule? A normal logic rule is a rule written like that. How do you read it? Well, it simply tells you that if a data point is associated with the labels a1 till ak, but not to the labels ak plus 1 till an, then it must be associated with the label a. And then, as I think the natural continuation, we were also able to extend these two requirements expressed as propositional logic formulas. So now we have like all of these nice models that can do quite like also powerful things, one could argue. Now, a problem that I faced when we did a couple of years ago was that we didn't have very meaningful benchmarks on which we could test the models that we proposed. So together with some collaborators, we decided to bring to life one of the first benchmarks for neurosymbolic models, at least in the wild. So we created the radar dataset. What is the radar dataset? Is an autonomous driving dataset which contains 22 long videos captured from the perspective of the vehicle, and each frame is annotated with bounding boxes of all the relevant agents in the scene, and each bounding box contains the agent in the bounding box, the actions the agent is doing, and the locations where the agent is. So for example, here you have a pedestrian that is moving away on the left pavement. You have a bus that is moving towards on the incoming lane, and then at a certain point, I think it reaches a junction. And then on top of this dataset, what we did was to annotate it with 243 logical requirements on the output space, which essentially express what are the set of labels that you can associate to each bounding box. So for example, you can have a traffic light cannot be red and green at the same time, an agent cannot move away and towards you at the same time, and so on and so forth. So once we had this data set, what we did was to actually test if neural networks were, like standard data-driven neural networks, were able to actually learn the requirements without imposing them, and we found that they quite often violated them. So here I just want to show you what I mean by a violation. So for example, here in the middle, we have that the neural network, which is a 3D retina net model, tells you that the traffic light is red and green at the same time. Here you have a pedestrian that is considered to be moving away, moving towards the vehicle at the same time, and it's on the left pavement and the right pavement. So as you can see, there are quite diverse, like what we found is that there are a lot of very diverse violations. And now imagine if you had a system trying to take decisions on the ground of these predictions. So this really showed us the need of requirements from a safety perspective. But then what we wanted to do was to ask a further question. So the question that we asked ourselves was, can we build a competitive neurosymbolic model whose predictions are compliant with the requirements? What do I mean by competitive? This is important. We meant a neurosymbolic model that was able to perform as well as a deep learning model, if not even better, by using the background knowledge expressed by the requirements. Again, after some time we managed to. So these are the charts that we got. So the baseline is a 3D retina net model, and these are different variations of our model, which was built simply by adding our layer, whose basic idea we saw in the hierarchical case, and adding our loss. So as you can see, all our models, all the different variations, were able to outperform the neural network. So we took the exact same neural network with 3D retina net, added a layer without any weights, and modified the loss as we saw. So in this scenario, the great thing was that our models were not only guaranteed to be compliant with the requirements, no matter what is the input, but we're also able to perform better. Now, I have a question for you. Can you do even better? We have actually organized a challenge on Rodar, which is the first neurosymbolic AI challenge at NeurIPS. We have two tasks. One is a semi-supervised learning task, where basically we ask you to just learn the bounding boxes that you have seen from just 3 videos instead of 18. And the basic idea is to see whether the background knowledge expressed by the requirements can help to learn also from the unsupervised videos. Then the second task is to build a model that is guaranteed to make predictions that are compliant with the requirements. So you can use the entirety of the training set, but now your predictions must be compliant. We also have prizes. So if you win either of the two tasks, then you get $1,000. And also the two winning teams will be asked to be co-author with us to for the NeurIPS 2024 report paper that they asked us to write. And also, if you're worried, like rightfully, about the GPU demand of this task, we are also able to provide some mini grants of $200 each. And finally, obviously, if you win, we can provide some travel grants. If you have any questions, please don't hesitate to contact me. I also put here the QR code that will bring you to our website, and participating should be a fun challenge for everybody. So I think we came to the end of my talk. I just would like to wrap up with some take-home messages. So the first one is that I think the main message, which I think I made clear, is that the requirements, elicitation, and satisfaction should be an integral part of any machine learning development pipeline. Given this, I think we should move to from a performance-driven machine learning to a requirements-driven machine learning. What do I mean by this? I think that performance should be just one of the many requirements that we have when we develop a machine learning model. It shouldn't be the only thing guiding us. Finally, we should stop thinking of requirements as something that limit the performance of our model, but we should start seeing them as vessels of background knowledge that can actually be used to improve the performance of the models themselves. And here I conclude my talk. Thank you very much.
Okay, great. Thanks so much, Eleonora. Great talk. So you have just a few minutes for questions. One is, how does it behave in out of distribution situations?
So this is, we didn't study it, but we have a theorem that says no matter what is the input, then the requirements are satisfied. So the requirements are satisfied. I think we need to study if it improves the performance on out of distribution inputs.
Did you try to apply such methods to language models?
Not yet is something that I would like to start probably next month. Like it's actually, language models are a really interesting problem, right? Because you have to take a decision based on the outputs that you have generated previously. So it poses also some nice theoretical questions.
Another one, increasing the number of constraints is better, right?
Normally, yes. So we have seen that, let's say, the more violations you have, the more improvement of performance you have when you add the constraint layer. So the more it has an impact. So normally when you add more constraints, you have more violations, and then it helps. Don't know if this answers.
Good. Okay, we're at time. So, oh, sorry, one more. What if with the increase of number of constraints, there's no feasible solution?
I mean, that's then I think more of a design problem, right? Because if you think from a engineering perspective, if your requirements are not satisfiable, then you're asking probably the wrong question. Like you should have at least a solution to your problem.
Okay, great. Well, thanks, Eleonora.
No worries. Thank you very much for inviting me. Stop.
All right. Start the next recording, Asim.
Yes.